One last but crucial question remains. Is in an Ethernet network, how does an end system learn the destination MAC address that it should write on a packet that it wants to send? Suppose Alice, which is the end system on the left, wants to send a packet to Bob, which is the end system on the right, who happens to be in the same IP subnet as Alice. The first thing that Alice needs to know is Bob's IP address, which will be the packet's destination IP address. We know how Alice learns this. She asks a local DNS server. The second thing that Alice needs is Bob's MAC address, which will be the packet's destination MAC address. To get this, she sends out a special request that states Bob's IP address. This request, which is called an ARP request, as we will see later, has a special destination MAC address, which is called a broadcast address, meaning that the request is addressed to all the end systems and routers in the local IP subnet. So every switch that receives this request broadcasts that it replicates it sends it out all its links. Now, eventually, the request reaches Bob. Now, when Bob receives the request, he recognizes his IP address and sends a special response, which is called an ARP response, as we will see later, which states his MAC address. Now, when Alice receives Bob's response, she learns his MAC address and is finally ready to send him a packet because now she knows both what destination IP address and what destination MAC address to write on her packet. Now suppose Alice wants to send a packet to Bob, who happens to be in a different IP subnet from Alice. As in the previous scenario, the first thing Alice needs is Bob's IP address, which will be the packet's destination IP address. And we know how she obtains this. She asks a local DNS server. Again, as in the previous scenario, the second thing that Alice needs is the correct destination MAC address to write on her packet. I would like you to pause the video and think for a moment, which is in this case the destination MAC address that Alice needs to write on her packet. It is the MAC address of router R's network interface that belongs to the local IP subnet. Now, there are two ways for Alice to learn this MAC address. The first way is called proxy ARP. As in the previous scenario, Alice broadcasts an ARP request that states Bob's IP address. So with this request, she's essentially saying, I need to send a packet to this destination IP address. Which destination MAC address should I use? Now, eventually, the ARP request, which is broadcast by all the switches that receive it, reaches router R. When R receives the ARP request, it recognizes that the target IP address belongs to a foreign IP subnet, meaning that any packet addressed to that IP address will have to exit the local IP subnet through R. Hence, R sends an ARP response that states its own MAC address. In other words, router R responds to Alice, here, use my MAC address. Now, when Alice receives R's ARP response, she learns the correct MAC address, destination MAC address to put in her packet, and she's finally ready to send her packet to Bob. Now, there is a second way for Alice to learn R's MAC address, and this is called default gateway. By configuration, Alice knows that R is her default gateway, meaning that any traffic that Alice sends outside the local IP subnet will exit the subnet through R. More precisely, Alice knows R's IP address. Hence, Alice broadcasts an ARP request that states R's IP address. She's essentially saying, my default gateway has IP address X, which is the corresponding MAC address. Now, eventually, the ARP request, which is broadcast by all the switches that receive it, reaches router R. When R receives the ARP request, it recognizes its IP address and sends an ARP response that states its MAC address. In other words, R is telling Alice, that's me, that's my IP address, so here is my MAC address. Now, when Alice receives R's ARP response, she learns R's MAC address, and she's finally ready to send her packet to Bob. Now, this whole thing I described is called the Address Resolution Protocol, or ARP. Its goal is to map an IP address to a MAC address. So if an end system like Alice knows the destination IP address that she needs to put in a packet, which destination MAC address should she use? Now, the ARP protocol relies on broadcast requests and targeted responses. For example, Alice broadcasts to everyone her request, her question of which is the right MAC address that she needs to use, and the right entity in the network receives this broadcasted request and responds directly to Alice. So ARP serves a similar role as DNS, however, it relies on broadcasting. So Alice sends this special request to this special destination MAC address, which is called a broadcast destination, broadcast MAC address. So this request reaches every end system and router in the local IP subnet. So if we compare ARP versus DNS, ARP relies on broadcasting, so it does not rely on any logically centralized map, and each entity knows its own MAC address and knows which ARP request to respond to, whereas DNS relies on the DNS infrastructure, which is essentially a logically centralized map that is stored in DNS servers. Now, to recap, we saw the following basic elements of an Ethernet network: address resolution protocol, which resolves IP addresses to MAC addresses; L2 forwarding, which is based on MAC addresses, which are flat; and L2 learning, which is how the forwarding tables of link layer switches are populated. Now, address resolution protocol is related to DNS, with the difference that ARP relies on broadcasting, whereas DNS relies on this logically centralized map, which is stored in DNS servers. L2 forwarding is related to IP forwarding, with the difference that L2 forwarding relies on MAC addresses which are flat, whereas IP forwarding relies on IP addresses which are hierarchical. And there is L2 learning is related to IP routing, with the difference that in L2 learning, there are no explicit routing messages exchanged between the switches. So here are two questions for you to think about. Could we get rid of IP addresses and IP routers and IP forwarding? Could all internet end systems have only MAC addresses and be interconnected through link layer switches? In other words, could the internet be one big IP subnet? What would be the consequences of that? And the inverse. Could all internet end systems have only IP addresses and be interconnected through IP routers?